Hi, my name is Toochi Onwuliri. I'm from COMSOL. At COMSOL, we develop and sell the COMSOL multiphysics software, which is a software for simulating real-world designs, devices, and processes. And today, I'm going to be talking to you about how multiphysics modeling and simulation benefits hydrogen technology development. And before I get started, I just want to say it's been very interesting meeting a couple of folks in this conference. I can see a couple of them here. And hopefully I get to meet some of you all before the end of the conference. I know time is running out for that, but hopefully I get to do that. But what has been extremely amazing is seeing some of the devices and equipment on display. Before yesterday, I'd only seen some of these things as computer simulation models. So it's been so exciting, having to see them. Oh, it's real, touching them and really, appreciating them. It's been really rewarding. And I can only imagine, how nerve-wracking it was for some of this, the production of these equipments, hoping that they work as expected, the way they were designed. Because there's a lot of unknowns to consider in production of some of these devices. Direct measurements is an issue. Sometimes it's impractical. And getting a physical prototype out can be really expensive, or even getting a working model out is really expensive. And that is where modeling and simulation can actually play a role because it gives us new insights into how our system is working before you actually get into production. And it's this type of understanding that allows us to have confidence in our devices, when it comes to safety, when it comes to performance, when it comes to cost, and also this kind of understanding that helps us reduce the time to market. So I'll begin by talking about, that's the first slide. Begin by talking about some of the processes involved in hydrogen technology. I mean, we know that it can be grouped into 3 stages, production, storage, and transportation, and ultimately usage. And one thing that all these processes involved in this value chain have in common is that they are all multiphysics in nature. So you have different physics phenomena interacting with each other and affecting each other. So take, for instance, storing hydrogen in a vessel, right? So you're going to have to pressurize the vessel, and that's fluid flow. But you also have to consider the thermal aspects because you are compressing the gas. But also, you have to take into consideration the integrity of your structure, so that's structural mechanics. So you see, you're going to need a tool, a holistic approach to actually understanding the behavior of this system simultaneously. All right, the software we provide, COMSOL, allows you to model different kinds of physics at the same time, so you can have any amount of coupling you want using the same workflow and in the same user interface. And this makes it extremely easy for you to test and analyze various designs in order to optimize performance and cost. So for the rest of the presentation, I'm going to go through some example models where COMSOL can be used throughout the value chain. And I'm starting with the production side of things. SMR is still a very popular method here. I mean, there's still some issues, unresolved issues like catalyst poisoning, and also, carbon deposition is a big deal here. And with COMSOL, you can model the effects of kinetics, pressure, concentration, and temperature distribution on the catalyst deactivation and reactor performance. Solar-based methods are also gaining in popularity, and it's not hard to wonder why when you step outside. But I kid there. But with solar-based methods, you have solar-based water splitting methods, and you also have thermal solar biomass gasification that you can model here. What you want to actually predict here is how efficiently the solar collector receiver system will produce hydrogen. And what you want to do with COMSOL, or what you can do with COMSOL, is actually model the ray optics. You want to model how uniform those beams are, because they affect the heat flux that is produced. So the uniformity of the heat flux affects how efficient hydrogen is produced with these solar-based methods. So I'm going to, try and focus now on some of the green methods because that's where we want to be. Hydrogen production by electrolysis is gaining popularity because it's one of the green methods. And with COMSOL, you can model all the electrolyzer chemistries, right? So whether it's alkaline, whether it's PEM, solid oxide electrolyzers, and many more, you can do that in COMSOL. And our customers typically investigate catalyst designs, the shape of the electrodes, and to try to optimize some other small details. So those are things you can do in COMSOL, and you can do that at different scales. So you can do that at the unit cell scale, where you can include the full electrochemistry there. You can also include multi-phase flow. You can also do that at the bipolar plate scale. In addition to the full electrochemistry and multi-phase flow, you can model the detailed geometry of the anodic and cathodic electrolyte channels. And at the stack scale, you can perform a system analysis there. You can include temperature, and you can also study the shunt current protection systems. That's some of the things you can do on the electrolysis side. If we switch gears a little bit into storage and transportation, there are a couple of ways you can use COMSOL in this area. If we look at storage, the metal hydride and base storage methods are some of the main approaches here. You can model them in COMSOL. A couple of issues still remain in these methods. You're looking at the weight and heat management considerations, make it a little bit more difficult for its widespread use, but you can analyze those in COMSOL. You can study the charge-discharge process in order to identify a couple of parameters you can modify. Another method that is gaining in popularity is frequently used is underground storage, and I must say I'm a little bit biased with this method because I'm actually a petroleum engineer by training. And there are a couple of options to consider in the underground storage. You can store it in salt caverns. You can store in depleted oil and gas reservoirs. You can store in different porous media rock formations. And some of the factors you want to model are like the geomechanics, the geochemistry. You want to look at the hydrodynamics. And ultimately, what you're looking for is the environmental impact assessment there. You're also looking at performance. So you can model all that in COMSOL and see whether you have a suitable storage site there. Now, if we move into transportation, and we're looking at things like transporting hydrogen through pipelines and flow and high-pressure vessels, and that's when hydrogen embrittlement becomes an issue because hydrogen is such a small molecule; it can diffuse into these containers and ultimately damage them. So you want to look at embrittlement. You want to estimate how long that vessel can last. Now, metering also is something you can look at. It's everything. So you want to make sure that your flow meters are accurate, and you want to make sure that they are optimally designed. Now, when we look at production by fuel cells, you can model that in COMSOL. We have a large variety of models corresponding to the different types of fuel cells. One thing about fuel cells is that they have higher efficiency than the traditional combustion engines. I know we're about 40 to 60%, and theoretically we can get to 94%. So there's still a lot of research availability here for improvements. So popular demand question or design questions you want to ask here is about you can model the full electrochemistry here. You can model the heat transfer here, and you can also model the transport phenomena here. So, and of course, you can do that at all scales. And at all scales, you can model the current density distribution. You can predict the performance at the unit cell scale. At the bipolar plate scale, you can identify areas of starvation and underutilization. And at the stack scale, you can look at the utilization and the performance on the stack scale. So, moving on, a user story I can share with you today is from Toyota. So the Toyota Research Center used COMSOL recently to optimize their fuel cell flow field plates. Quite a mouthful there. So they accelerated the development of their fuel cells with COMSOL. Recently, the goal, as I said, was to optimize these plates. And there are a lot of ways to do this, okay? And so what you need is kind of a tool that you can test different configurations. And so they tested a couple of configurations they had, and this allowed them to greatly reduce the amount of physical prototypes that they were going to build. And ultimately, the prototypes that they built, they were able to confirm that these models they choose actually increased the power output and outperformed baseline conventional designs. And ultimately, this was due to better fluid distribution and uniform reaction rates because they were able to model this in simulation before they moved forward. So that's a user story. I mean, I can share that more. You can meet us there if you want to learn more about that. But as I conclude, really I want to share some of the, I like countdowns, right? So I want to share top 3 reasons, why, COMSOL is well suited for hydrogen technology development. And the first reason is really that multi-physics capability of COMSOL. You can include whatever physics phenomena you want in the same model, right? And it allows you, it gives you the freedom to do all that. Number 2 reason will be our consistent or the same workflow. So whatever physics field you're working in, whether it's electrochemistry, structural mechanics, electromagnetics, it's the same workflow. So you learn the general workflow, and then you can apply it for any physics. So it makes it easy for you to learn COMSOL. And the next reason, number 3, will be the consistent user interface, right? So for whatever you're working in, it's the same user interface that you'll be working in. And for example, you were seeing a ray optics model, now you're seeing an electrolyzer model. You can see it really looks the same. If I show that embrittlement model, same user interface, same workflow, and I show a fuel cell model, same interface, same workflow. And this helps, collaboration really, because if teams are working on the same device but working on different aspects of that same device, they can ultimately come together at some point, share models, work with each other models, and make it easy for that kind of collaboration. So I'll conclude the way I started. I started by saying that COMSOL can, multiphysics simulation can be utilized throughout the hydrogen technology value chain. And over the course of the presentation, I've tried to show that COMSOL has been used, can be used, and is still being used at this time for different aspects of the value chain. And this is because a variety of phenomena can be analyzed, can be modeled in COMSOL. So if you want to learn more, I have some brochures that I want to share, so you can meet me at the side if you want to learn more about COMSOL. You can visit us at our booth. We're just close by, CO8. Or you can get us at our website, COMSOL.com. So feel free to reach out if you have any questions. I'll be at the booth. My time just ran out. All right, that's me.